All right, well, here we are, the morning of the flying pig. Needless to say, it has to be on a string. I did have a student once that was quite disappointed. He thought the pig was actually going to fly around for him. And when asked where I bought it, I showed her the catalog, and they found that you could get a hat, a trucker hat, funny enough, a trucker hat with little wings on it, pink wings. And she actually said, if I wore that, could I fly into that? And that was kind of the response from the rest of the room. They said, oh. He's one of the people who didn't really think for themselves. I encourage you to do that. His wings actually do flap though. And he does fly. Now, do you think the wings are just there to make it look cool? Or do you think they do something? Think they do something, Connor? How could we tell? Turn it off and see what happens, right? Do you notice any difference?
It's closer to the middle.
He does seem to lose speed, I guess you could say. Does seem to lose energy. So oddly enough, to be perfectly honest, I don't know how, but those wings are actually helping the pig fly. So it's kind of. Alright. So there's a little bit of lag that goes with it there. Just in time, Josh.
Take it down.
We almost named the pig after you.
Why?
I don't know. It's turning right here. His name is Floyd. Wow. Okay, so the purpose of the flying pig is to show the net force for a conical pendulum with mv squared apart. So when the pig flies around, that is what's known as a conical pendulum. A cone is like pointy, like top of a granary kind of thing, right? Pendulum, the swing back forth. So equivalent, you need to fly big or equivalent, blah, 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 blah. Oddly enough, it took me about an hour to create that little device up there. Not this morning, but it did take me quite a while to figure out how to do it. In my old room, I could actually mount to the ceiling. When I moved in here, I had to figure out a way to do it. So that's how the system like come up. And it actually works not too bad considering it's well. So discussion, when an object travels at a constant speed along a circular path, we say that as uniform circular motion. If its speed were changing, then its motion would not be uniform. Any object moving in uniform frictional motion is accelerated toward the center of the circular path, and this acceleration is called centripetal acceleration and equals v squared over r, where v is the speed and r is the radius of the circular path. Since the net force on any object equals ma, during uniform circular motion, the net force called centripetal force equals mv squared over r, and is directed toward the center. This is what happens when an object suspended by a string moves in a circular path, which is known as a conical pendulum. The string of a conical pendulum shoots out a right circular cone. In this experiment, you will measure the speed of the object that comprises the conical pendulum and show that the net force is actually mv squared per. So pre-lab analysis. Draw the force vectors, a 3-by diagram that act on a conical pendulum. Ignoring air resistance, note there are only two forces that act on the pendulum. Bob, in this case, the pig. One is mg, the force of gravity, and the other is a string tension. So you have this little picture here, I believe, right? And you'll notice that there is a mg down, and then this is T tension in the string. Step 2 says with dashed lines, show the horizontal and vertical components of T. Also label theta between the tension T and the vertical. So I'd like you to draw in these components right here, and I see that I'm going to have to, I think I have the recording off there, so I'll pause there while people that are watching at home caught up. That is our formula, P equals square root Rg tan theta. Under procedure, it says, set the flying pig. Note anything that flies in a circle will work here, whether it be a toy airplane, toy flying pig, flying cow, whatever. Be careful not to damage the delicate wings as you click them into that fixed wing position. Ask your instructor to check your pivot before switching on the battery power. Carefully hold the pig by its body and give it a slight shove about 30 degrees vertical, just enough so that the pig flies in a circle. The goal is to launch the pig tangent to the circle of flight. It's better to launch it too easy than too hard. If the pig does not fly in a table circle in 10 seconds, so carefully grout and try launching it again. Step 6. Once the pig is up and flying in a circle of constant radius, Measure the radius of the circle as accurately as you can and express your answer in meters. In other words, do this. Now, how are we going to measure? Don't fall asleep now, you're all getting hypnotized, I can see it. How are we going to measure the radius of the circle? Any ideas? With a measuring stick, says Josh. Excellent.
Put a string on the bottom of it.
Put a string on the bottom of it?
And put a weight, a really heavy weight.
Okay. So, you're suggesting something like this kind? And then do what? Austin, any ideas? Better? Here's the problem solving part of the day. Bailey? It's not an easy question, is it?
Unless you get someone to stand right in the middle, I think.
And do what?
Hold a meter stick and have
Like literally stand like right underneath and do this?
no, like have the pig and sitting next to one stand in the middle and measure.
Like, oh, like in the middle and
Yeah.
That's dangerous.
John, any ideas? I've had various ideas over the years.
Is it with the cone? Like a cone?
What do you mean?
Like you find...
Well, we're trying to find, right? Okay, so we're trying to find that R there.
So you measure the length of the string
Find the angle.
and... oh, you don't have the angle.
Mark suggests to measure the length of the string and then try to find the angle. And that would give you this, that's true, but how are we going to measure the angle?
You can say...
Slightly change too.
Theoretically, it should be sort of reasonably constant.
You could politely ask the pig. You're like, what's your radius?
What's your radius? Okay, well, here's another good question. Does it matter how hard I push him? Does that change the radius? I'll just give him a little push here. See. I hardly moved him at all.
That's the right?
Now, if I give him a good shove,
Whoa. The radius is dependent on the applied force.
it does seem to be, doesn't it? So I do have to sort of tend to give it a constant one. I've gotten pretty good over the years at giving it the right push that I want. I was in here yesterday practicing. Although it does tend to, it looks like, once it sort of gets going, it tends to sort of find entropy maybe, right? Oddly enough. It tends to find that sweet spot, doesn't it? There's some chickens. You will notice there, you might not see it, but the pivot itself actually has a little bit of a bend to it. You guys probably can't see it, but as it swings around there, it's actually got a bend to it, so I'm guessing that that has a fairly big point in what that angle is. Right? Like it sort of goes to that. I've had a couple of ideas over the years. Some student ones that I don't even think I have them anymore. Well, see. The kid took it home for another purpose and never brought it back. One? Was that? That's okay. Not gonna lie. One person suggested mounting a laser pointer to the bottom, pointed straight down. Excuse me. And then we can see the circle on the floor and try to do that.
Get a really big pencil and a really big tape.
Like a giant pencil. I like that idea. I'd never heard that before, so I actually tried it with tape on the laser pointer. And unfortunately, what happened was the laser pointer itself didn't hang straight down, and in fact, went out to the side as well, right? So in fact, it was like pointing out there, which really wasn't an accurate measurement. So what I've done is, if you actually go into Mr. Smigelski's room, which is my own classroom, there's a spot on the roof where I used to mount that, and you can actually see the pencil mark on the ceiling. Okay? And what I did was I took that laser pointer, like this, and I pointed straight up, and then when I get the pig going, I bring in the laser pointer. Am I okay here? Yeah. Bring in the laser pointer until it just breaks the laser beam, and then we had a kid climb up there and we actually mark that distance. Okay, so that's how we figured out what the radius was. So if I just give you that number, is that okay?
Can I go get my laser?
Do you have a laser pointer? In your locker?
Yeah.
All right, go ahead. I've been meaning to ask Mr. Wooders, one of the principals, for usually they confiscate for kids. They were big back in the early 2000s. Every kid had one, you know, fun. We confiscated them all the
My
time.
favorite thing is going to concerts and there's like that one guy who's got laser pointers.
No, they're
Like,
really
he up
good.
at the screen and it's like, what are you doing?
Idiots, eh?
Yeah, man, outside.
Yeah.
And you wanna write some stuff down.
So, I will tell you that the radius that I've gotten before is, I've got two. I've got 0.525 and 0.58. So let me see what Shane's laser pointer comes up. We've got time. How are we going to measure that horizontal distance?
The string.
Like in the old days, like I could measure it clearly from the top where it was mounted on the roof, right? But here now, I've got to measure from there. I've got to go sideways over some sort of magic point. I guess we could get someone to climb up with a meter stick. Right? Hold it there. The meter stick would thread it. Right? We could sort of estimate too. Right? Just doing this. You want to try this and see? I need someone. Come on up here, Josh.
Heck yeah. Am I, holding a stick?
You're home. Well, you stand right over here. Maybe that, I'll get her going, and then you can kind of slide in there and see. Okay? Heads up. Okay, so now you got to put the meter stick in the center.
Let's go underneath it.
I know.
It's kind of like doing the limbo there. I'd say like right about here.
From underneath it. Now look up, look straight up. Look in the center of the rack.
Look at that.
You gotta make it level.
Okay, you're nowhere close. Stick your head up there.
It's like right above.
Yeah, I know.
Go underneath.
You want a chair?
What am I supposed to be measuring here?
You're trying. Well, he's lost his. We could do this too, right? We could do this, right? And then you find the center. Here, I'll see you. Right? There's a mistake. Want to slide over so you're right in the right spot? Okay, how you feeling with that?
Sure.
Okay. Well, no, you got a hold there.
Well, right.
Put that one down.
And maybe just put this down a stitch. There you go, right over there. Okay, we're good? John? Austin, you guys are in line, that's pretty good? Okay. Both there?
Yeah.
64.
64.
64 centimeters.
Pinata.
Okay, now, hold on, because we're going to need you again. Would you want to try it, Shane?
Yeah.
Huh? Oh, okay.
I know. That's what I bought.
Okay, so like if we go like this, the only thing is that this isn't right from, well, that's pretty close, isn't it? It's pretty close to the center, I mean. Okay, come on, this is shading. So you're gonna hold it about there. Right, and you're gonna have to move it back and forth, line it up so it's right in line with that groove there. There you go, okay. And you're gonna have, now, does he have to hold it straight up and down? He does, right? Like, you can't be doing this, right? Or that, right? It's gotta be straight up and down. Okay, I'm gonna put the brake, we'll see if we can get it to break the lead. You got it way over at an angle now, I can tell.
Oh, with 2 hands.
Yeah, but I don't think they're holding it straight, because I can, from my angle right here, it looks to me like it's, like the pig is going. Yeah, I think, which one do you think is a better method?
I think it's good.
No judgment
You need
here.
a straight holding apparatus.
Yes, I think you're right, because when I'm standing here, I can see where it is. It looks to me like it's about this main, that far to the left. You're right. I think we're gonna go with the meter stick. Yeah, I think so. Okay, so what distance was it again?
60.
Let's go right down. 64?
Yeah.
Okay. That means I gotta change my notes here. All right. Okay, so we're gonna say the radius of said pig is 0.64 meters. There are several ways to determine the angle that the stream makes with the vertical. Using a protractor may not be practical as other methods you may devise. Describe your method and then record your value for theta, include a sketch. So we've got our cone like this. This radius here is 0.64. We're trying to find that theta. What's the easiest way to find the angle? It's easy. Martin had an idea before. What was your idea before, Martin? Very length of string, because that's easy to measure, right? .79. Now, where is that on this diagram? Is it this one? How come? Because once I swing it, then the string is that length there, isn't it? Right? Found a mistake. So that's going to be opposite hypotenuse. Sine theta is going to be the opposite, 0.64, 0.79. So theta is the inverse sine of that. And don't be in radians. $54 degrees? Okay. Step number 9. So then it's on the next page where you write theta value, right? Step number 9, using the values for r and theta that you determined in step 7 and 8, compute the theoretical speed of the pig using the formula you derived for the speed in steps 5 and 6. Remember, this speed is based on F net is equal to mv squared over r. So the formula that we came up with was v was equal to the square root of rg tan theta. The radius of orbit is 0.64, 9.8 times the tan of 54. Make sure you take the square root of it. So this is to come up with the speed of the pig. Floyd. No, not 5. $8.63? Oh, did I take square root? I don't think I did. 2.93. Do we agree? 2.93? Yeah? Did anyone try it? Did anyone do the math?
Yeah.
Okay, thank you. Okay, so now we have to actually, step 10 says in step 9 you calculate the theoretical speed of the pig. Now let's actually measure the speed of the pig and see how these two values for the speed compare. Since the pig flies in a circle, the speed is the circumference, 2 pi r, divided by the time, t for 1 complete revolution. To make your measurements of t more precise, measure the time it takes the pig to take 10 revolutions and divide by 10. So just like we did in our own lab, and we're going to come up with the actual period. So get your devices out. If you don't have one, that's fine. We'll get you a time. I just want to get more than one time measurement. Does anyone want a stopwatch? All we need is 3 or 4, so we can. I'm waiting for like the all clear.
I got one.
Everyone's good to go? Okay, so I'm going to give him a push, and then when I say start, then I'll start counting, right? So I'll probably start when he gets over to here, right? So just be ready. So I'll go around a couple times, so we get, go on in a sort of good circle. Okay, next time around, and start. 1, 2, 3, 4, stop on 10, 5, 6, 7, 8, 9, 10, stop. Yeah, 10, stop. 10.
I had 16, point three.
Okay, just fire up, give me 3 or 4, 16 point what? 8?
16.57.
Okay, so there's 4 there. So let's just find the average of those. 16.37, 16.8, 16.57, 16.47. How about, can we just, because obviously this is fairly loosey-goosey here, can we just say an average of 16.5? Are you good with that? That's probably pretty close to that anyways, right? Okay, so that's our time. So then we're going to take our period. Big T is going to be our 16.5. We're going to divide by 10. And that gives us a period of 1.65 seconds. Right? Okay, now the velocity then is the circumference divided by the time. Velocity is 2 pi r divided by time. So 2 times pi, and the radius of our circle was 0.64. All over 1.65. And we should get an answer that's what? Pretty close to 2.93. I don't have a pi button on here. What do we get? So I get 2.44. Did you get something close to that? Is that reasonably close? It's not bad, eh? It's not bad. Step 12 says compute the percent difference. This is something that we did in the projectile motion lab. Compute the percent difference between the value for the speed you computed in step 9 and measured in step 11. Use the calculated speed as the known. So this is the, in other words, the actual here. So you're going to take the difference, which was 2.93, am I right? Yeah, 2.93 minus 2.44, which is a difference of 0.49, and we're going to express that as a percent of the, it says to use the calculated speed as the known, so we're going to divide by the calculated speed of 2.44, and we're going to multiply by 100. It gives us our percent difference, and it's about 20% error, which is fairly high, but how accurate were our measurements? Of all the measurements that we did, what was likely the most accurate? Yeah, probably. And even that might be debatable, Mark, because I measured
Go ahead.
I measured straight down, but I measured to there, right? And I guess the question is, do you measure to like the bottom of the pig? So I measured to the bottom of the pig. Come on. I get like 87. So that's going to make, let's just kind of quickly estimate here. That's going to make that longer, which is going to make that angle slightly less. But it's going to change this number. No, that's the only one, right, that it changes? So it'll change the angle slightly. I don't think that's going to make a huge difference. Okay? The time is probably pretty accurate. How accurate do you think that radius is that Josh came up with? I mean, we're ballparkists, right? What did we say, 64? Yeah. That's like right there. Do you think the pig was flying like right up to there?
Yeah, to be fair.
Yeah? Regardless, we got an error percent of 20%. Not too bad considering all the different errors that could possibly be there. Okay, so post-lab analysis, what techniques for measuring R and theta would you recommend for best results? What might be, now that you've sort of seen in action, what would be some other ways now that you can think of that might measure the angle or the radius more accurately? Think technology.
Put a thing on the iPhone on the
Put a thing on the pig, iPhone on the pig?
yeah, so you can see the angle. Go on ahead.
GoPro.
Oh.
Go on the
Well, that would be cool to put a GoPro on the pig. What if you had like a white screen on the back, right? And you marked 0, right? And then you had someone hold a stick or something around it like this until it matched the angle, right? Someone over there confirmed that it matched the angle, then you take that away and then you measure. That might work.
Do a Mythbusters thing, put a piece of cardboard on top and put a camera facing straight up and you can see.
Oh, like you put a camera down here,
Yeah.
look up, and then, okay. You can put it behind.
Both the angle and the radius.
Yeah. Yeah. So this, I think with some technology, you can probably come up with some better way. Are you going to get much better than 20%? You might get it down to 10. Right? Yeah. So there's various different ways now that you've sort of seen it in action that you can come up with. Okay. A couple more questions there. Number 2, what do you conclude about the magnitude of the string tension compared with the weight of the pig? For uniform circular motion, the tension will always be less than, the same as, or greater than the weight. So here we have the weight straight down. How does that match the tension? Which one are they? The tension will always be less than, the same as, or greater. Martin says greater. Why greater, Martin? Right? There's the T. There's the mg, right? In fact, the Ty is equal to the mg, right? So yes, Martin is right. The tension in the string is greater than the weight. The tension in the string is greater than the weight. What do you conclude about the direction of the net force that keeps the flying pig in uniform circular motion? Well, I don't know. Can you come up with anything from the lab itself, or do you just know? What is the direction of the net force? It's where? Towards the center. It is centripetal. Towards the center. Center seeking. Number 4. For uniform circular motion, the centripetal force will always be less than, the same as, or greater than the tension in the string. So same picture. Tension, mg, ty, tx. Now the centripetal force is going to be equal to the what? The tx, is it not? The centripetal force is equal to the tx. So the question, the centripetal force will always be less than, the same as, or greater than the tension. The tx, the fc, will always be less than the tension, right? Because it's the x component of the tension. Step number 5, how does the pig overcome air friction? Because he does. The wings do something. I would like the Mythbusters to investigate. The wings clearly do something. What do you think they do? Do you think they create some sort of small amount of lift force?
They go up and down.
Well, they go up and down, you're right. They make us laugh.
The outside wing probably.
You think so? You clearly saw when he's flying with the wings that. You can feel a bit of a breeze back there.
And now it's question to like,
Say again?
like if you do it without the weight, he always, his head faces outward.
He does tend to, he spins differently, doesn't
He
he?
spins like a, like he's spinning.
That's not really a very good circle, is it?
So we can kind of just keep them straight.
Kind of stabilize them a bit, don't they? Yeah. Now his head is facing the mark.
His wings were made out of something else they were.
They're just like, there's nothing to them. He definitely is more stable. He's facing where he's going. I'm not sure why it's a keen pig. Battery up. Non-gender specific is battery operated. Floyd, yeah. I may be a misnomer. Any sources of error?
Yeah.
Everywhere. Alright. So that's all I have for you today. It'll be one thing. Please tell all the grade 11s how exciting it is so they all take grade 12. This is one thing. Who wants to come up there and take down my device? Here, you'll have to actually look at that. Okay. And those are just nice and thick, come on. No, give me that. Have it out.
Star.
Put out. Yeah. Okay. Now, oh, hang on. That's gonna come down too. Okay, so take this. Yeah, and the ones on the right hand side, straight up, like the ones here. Yeah. No, well, the one that's facing this way. No, that's not, right. The other one, yeah. Okay, that one there. Loosen that. There you go. Don't drop now. Yeah. Okay, so you guys have the rest of the period. Do some circular motion problems. If you haven't completed that first pre-test, you should do so. Thanks, Mike. And then Monday we'll deal with some banked curves. Trying to liberate my pig.
You don't want to stand it in. We're not hanging it.
No.
You're so loud for it.
Oh, I wasn't closer. Stop.